The video about solenoids on Ohm's law generated quite a few good comments, and it would be a shame not to make a follow-up video. To recap, we found that Ohm's law is pretty accurate, but there are some variables. One of the most important ones is measuring the voltage right at the solenoid leads rather than somewhere else like at the power supply. Another variable is that if the solenoid stays on for a while, the heat generated inside it changes the resistance of the windings, and this obviously changes the current that is going through the solenoid. So let's finish the experiment and leave the solenoid on for, let's say, 5 minutes and see how much its resistance changes.
Okay, so we have the setup as before. We have a stone cold solenoid. The leads going to the multimeter are right now shorted, and the ohm meter is showing 1 ohm. That's something that we'll need to subtract after we get the measurement for the resistance of the solenoid. So we connect the lead and it's showing 36.3 ohm, and remember we have to subtract 1 ohm. Now let's switch all that to the voltage range, 20 volts, and connect the power. And we are seeing 11.7 volts going to the solenoid, and the power supply is showing 0.325 amps. But now let's wait for a little while, start the timer, and see if these values change. Alright, so it's been 5 minutes and the voltmeter is showing 11.75 volts. The amps are lower now at 0.296, and if we divide the voltage by amperage, we are going to get around 39.5 ohm. The solenoid itself is warm to the touch, but just warm, not hot. Okay, so now let's take the power off and switch the meter to ohms, and we are getting 40.5 ohm measurement, and it's going down. Alright, I guess we have all the figures we need for the calculations.
So what do we see? When the solenoid is cold, then we measure the resistance with an ohm meter and we get 35.3 ohms. With the Ohm's law we get 36 ohms, a little bit bigger but still within 1 ohm. When we wait for 5 minutes, we are getting quite a bit higher resistance. 39.7 ohm comes from the Ohm's law and 39.5 comes from the ohm meter. Very close, and that difference is because presumably of the temperature, and we can even try to estimate by how many degrees Celsius the temperature changed, because we know the temperature coefficient of resistance for copper, which is the usual material used for windings. So the formula is like this, and the coefficient alpha for copper is 0.004. So let's just use those numbers and we get the following. We need to take the bigger resistance, 39.5, divide by 35.3, the resistance when the solenoid is cold, subtract 1, and we get 0.12, and that should be equal to 0.004 multiplied by delta in the temperature. From this, we are going to get that the temperature delta is around 30 Celsius, which is kind of confirmed, or at least consistent with my observation by touching the solenoid, and it was kind of warm, but not too warm. Unfortunately, we really cannot confirm it any better, because there is no way I can stick in a thermocouple inside the solenoid without completely disassembling it. But nevertheless, that's kind of an interesting calculation that may provide a rough estimate for how much the temperature actually changed. And last, but certainly not the least consideration, brought up by one of the viewers, Radu, that here I'm testing a known good solenoid. And so I expect with the heat the resistance to change somewhat, but that would be it. If the solenoid is bad, for example, it has faulty insulation, then the current and subsequently heat may change the things dramatically. For example, it might result in intermittently shorted windings, changing the resistance a lot, and we will see really different currents. And basically, with such solenoid, all the bets will be off, even though when the solenoid is cold, it might still show resistance very close to the specifications. And this actually demonstrates a deeper mathematical logic of resistance checks, that if we see bad resistance measurement, it means that the device is bad. But if the resistance measurement is good, we cannot really say that the device is good. And this is an interesting topic, and I hope to expand on this in a future video.